if you remember way back in chapter 0, when we started the class, we went through and did a section on curve sketching where we found the domain and the vertical asymptotes, holes. We found the x and the y intercepts, and we used all those to draw a sketch of what the graph is. So in 5.1, we're doing the same thing. The only difference is we're going to combine with that what we now know about finding relative mins and relative maxes and points of concavity, and that can make our graphs even more accurate. So we have this curve sketching recipe, right? Most of this should seem really, like I said, we did these first 5 steps already on those lessons, again, way back at the beginning of the year, right? Find a domain, we reduce f of x. Once it's reduced, we can tell if it has vertical asymptotes or holes. Find the x and the y intercepts, end behavior, right? Look for horizontal asymptotes. But then now the 6 and 7 are now adding in the calculus stuff that we've learned, right? Find increasing, decreasing intervals and relative extrema points. That's using the f prime number line. And then find concavity and points of inflection. That's using the second derivative number line. So combining all this together, no new concepts, we're going to combine it all together to draw the sketch of curves. If you remember right, we had one of these on our very first test we took. We had actually a couple of problems like this. They just did not include relative max, relative mins, or concavity because we didn't know that yet. Okay, so let's go through this example. So domain, let's start with that. So to check my domain, I'm looking at the denominator. What can x not equal? Well, x squared plus 1 is always positive. It never equals 0. So the domain is all real numbers. X can be anything. What that means is that there are no holes and there are no vertical asymptotes. Okay, let's find the x and the y intercepts. So to find the y intercept, we plug 0 in for x. So really I'm just finding f of 0. If I plug 0 in, I get 0 over 1, which is 0. So I have a y-intercept at 0, 0. To find the x-intercept, that's when y equals 0. Well, the only time, if you have a fraction, right, the only time a fraction can equal 0 is if the top equals 0. So that's a 0, which we already had, right? If it's, the y-intercept is 0, 0, the x-intercept is also 0, 0. End behavior. To check end behavior, compare the degree of the top to the bottom. So if you look at that one, the top's bigger than the bottom. That means it's either going to infinity or negative infinity. Let's real quick just check on that. As x goes to infinity, we want to say what y goes to. Well, if I plug in positive numbers, like really big positive numbers, I'd get a positive on top and a positive on the bottom. So that means it goes to positive infinity. I'm going to kind of drop this down here. As x goes to negative infinity, what happens to y? So as I go to negative infinity, I get really big negative numbers on top. I get a negative, I get a positive. So it goes to negative infinity. So over here, let's put the information we have. Not a lot, but we know it has an x and y intercept of 0, 0. We know it's got to be going out this direction, forward to the right, this direction to the left. So if we just use what we knew about curve sketching from the pre-calculus stuff we reviewed, we'd be pretty stuck there. There's not a lot of specifics there. So we're going to see what we can learn now by using calculus. So we want to find the relative max and relative mins and the points of inflection. So let's do our first derivative number line test. Kind of nice. They have the first derivative already done for us up here. So remember, I've got to find my critical numbers. So when is it undefined? Well, x squared plus 1 is never equal to 0, so it's never undefined. When is it equal to 0? Well, there's my two factors up on top. So when would they equal 0? So that would be at x equals 0. X squared plus 3 does not equal 0. It never does. So really, I just have one critical number at 0. And now I just got a test on either side of it. So I'm going to pick a number smaller than 0 and plug it in. So you could plug in -1, for example. If I plug -1 in the top, I'd get, this would be a positive right there. This part would be a positive, so I get a positive on top. If I plug it in the bottom, I get a positive. If I plug in +1, I get a positive, positive, positive. So if you look at this, there are no relative max or min points. The only possible one was at 0, and it goes from increasing to increasing, so it can't be either of those two. Okay, last thing is points of inflection and concavity. So let's come up here. I'm going to put my second derivative number line up here. Okay, find your critical numbers. Again, when is it undefined? Well, this is never 0, so we're good there. The top part, those can both equal 0, right? I'm going to have one at 0 And if I solve x squared minus 3, if I add the 3 over and take the square root, I get plus or minus the square root of 3. So I got a positive square root of 3 and a negative square root of 3. So these, 0 plus or minus square root of 3, those are my possible points of inflection. Now I just need to plug in some numbers and test. So let's try like negative 2. If I plug in a negative 2, that'd be a positive 8. That'd be a positive. That would be a positive. So let's concave up on that interval. Let's pick something between negative square root of 3 and 0. You can do like negative 1. That would be positive. But this one now, negative 1 squared is 1 minus 3 is a negative. So I have a negative, sorry, a positive times a negative, which is a negative, over a positive. So that comes out to be a negative. If you plug in 1, this would be a negative, negative, which makes it a positive, positive. If I plugged in 2, I'd get a negative 8, positive, positive. So I end up with a negative up there. So we do have some points of inflection. Let's write these down. There's going to be a point of inflection at negative square root of 3 something, at 0 something, and at positive square root of 3 something. So let's plug these. Now I want to find what the actual points are. So let's plug it back in our original function and find out what we end up getting up there. I plug in a negative square root of 3, we'd end up with 2 times negative square root of 3 cubed over, plug it in the bottom, negative square root of 3 squared would be 3 plus 1 is 4. So we end up with that. You can reduce that down to be 2. So we end up with this. We end up with square root of 3 cubed over 2. Negative square root of 3, sorry. And you could plug that in a calculator, figure out what it comes out to. It's about a negative 2 point something. We're not going to, you could do that calculator and get the precise thing. I'm not going to worry about that though. Hey, we have to know this point's at 0, 0. If I plug in a positive square root of 3, you get the same thing. The only difference is it's a positive square root of 3 cubed over 2. And that again comes out to be a positive like 2 point something, 2.1, 2.2. Okay, let's put all those points on here. So I know that there is a point of inflection at negative square root of 3, which is negative 1 point something, and negative 2, somewhere down in that area. I'm just approximating at 0, 0. And at positive square root of 3, positive square root of 3 cubed over 2, somewhere up in that area. Okay, I know that it's increasing the entire time. It's monotonic, so it's increasing across the whole thing. Look at the concavity though. From negative infinity to negative square root of 3 is concave up. So this has got to be something like this, concave up. And then from negative square root of 3 to 0, it's concave down. Goes from concave up to concave down. From 0 to square root of 3, it's concave up. And then from square root of 3 on, it's concave down. So the graph's going to look something like that. And I believe this graph is symmetric. If you were to plug in like 1 and negative 1, I think you get the same thing back out. It'll look symmetric when we get there. Okay, so really we're doing the same thing we did before with curve sketching. All the same steps. All we're adding is finding relative max and mins and intervals where it's increasing, decreasing, and concavity and points of inflection. All right, let's try another one. So we got this one. I got f of x equals 3x minus 2 over x squared minus 2x plus 1. We'll start by finding the domain. If I factor the denominator, factors would be x minus 1, x minus 1. So x cannot equal 1. Okay, if it reduces, let's see. So 3x minus 2 does not reduce with x minus 1, so it doesn't reduce. That means at x equals 1, there's a vertical asymptote. If you want to make a note of this also, it's going to be even because it's really x minus 1 squared. So that means they're both going to, as the graph approaches that vertical asymptote, they're either both going to go up or both go down. 1 was the only restriction on a domain, and it was a vertical asymptote. That means that there is no hole. All right, let's find the x-intercepts and the y-intercepts. X-intercept, you find out when the top equals 0. So when does 3x minus 2 equal 0? So you add the 2 over and divide by 3, so 2/3. Y-intercept, plug 0 in for x. If I plug 0 in for x, I get negative 2 on top and 1 on the bottom. Okay, let's put all that information on the graph. Oh, and behavior. Let's do that real quick. If you look at end behavior, the degree of the top is 1, degree of the bottom is 2. So the bottom is bigger. So there is a horizontal asymptote at y equals 0. Okay, let's put all the stuff on the graph here. Got a horizontal asymptote at y equals 0. Got a vertical asymptote at x equals 1. There's a point at 2/3 0. That's somewhere in that area. There's a point at 0, -2. And I think that's all we got so far. So now let's do some calculus. We want to find the relative max, relative mins, and the points of inflection. So we'll start with the first derivative, find the relative max and relative mins. I'm going to do my first derivative number line up here. Find the critical number, sorry. Mine went blank there for a second. So let's start here. It's undefined at x equals 1. But if you look at this one, x cannot equal 1. So x equal 1 is not a critical number, but we do need to put it on a number line because it's undefined there. The other time is when does it equal 0? So -3x plus 1 equals 0. You solve that, and you get 1/3. So put 1/3 over there. So just remember that 1 cannot be, 1 is not a critical number, so it cannot be a min or max, but we still need to check the intervals. Okay, so let's plug in some numbers. I'm going to plug in 0 first. If I plug in 0, I get 1 over -1, so I end up with a negative. If I plug in something between 1/3 and 1/2, I can plug in 1/2. If I plug in 1/2, I would get a negative on top and a negative on the bottom, so it would be a positive. And then plug something to the right, plug in 2. That'd be a negative over a positive, so it's a negative over there. So there is a relative min, right? It goes from negative slope to positive slope at 1/3. So relative min at 1/3. I don't know the y value yet. We'll have to find that. There is no relative max. Even though it goes from positive to negative, there's a vertical asymptote at 1. So there is none of those. Okay, let's do our second derivative number line test now. Find out where our points of inflection are. So when is a bottom equal to 0 at 1? That's not a possible point of inflection though, because it's a vertical asymptote right there. Okay, and then also at 0 up here. So let's check. You can plug in -1, so it'd be a negative over a positive. You could plug in 1/2. That would be a positive. And you could plug in 2. That'd be a positive over a positive. Okay, so I've got a point of inflection at 0, and I already know that point. Normally you have to plug 0 in to find it, but I already know the point is 0, -2. Let's figure out what that relative min is. If I plug 1/3 back into my original function, I'd have 3 times 1/3 minus 2 over 1/3 squared minus 2 times 1/3 plus 1. So that would be, what, 1 minus 2 to get a -1 up on top. On the bottom, that'd be a 1/9 minus 2/3. That'd be minus 2/3, get a common denominator, it'd be 6/3. So that'd be 1/3 plus 1. So I think that is 4/3. All right, sorry about that. This actually comes out to be 4/9. So it's -1 over 4/9. So if you times by the reciprocal, it ends up being a -9/4. So this is -9/4 there. That's a -2 1/4. So 1/3, and it would be somewhere in that area, just a ballpark. Okay, let's see if we can put all this together. So we know that it's got to be a min right here, and it's going to be concave down until I get to 0. So it's got to be concave down. So something like this, maybe. And it's got to get closer to my horizontal asymptote here. Probably some concave down. And then it's got to change to concave up at 0 until I get to 1, it's going to be concave up. So it's coming up this direction along that vertical asymptote. Over on this opposite side, we know this asymptote is even, plus we know that it's concave up, so it's got to be curving down that direction, down along our horizontal asymptote. So again, this is the calculus part, relative mins, relative maxes, points of inflection. Just add some more information that makes it easier to make our graph more accurate. Okay, let's do this last one that has a radical in it. So if we start out our domain, that's when the bottom equals 0. The bottom will equal 0 when that equals 0. X squared plus 2 will never equal 0. So domain is all real numbers. That means there's no vertical asymptotes. There's no holes. Y-intercept, plug 0 in for x. If I plug 0 in for x, I get 0. X-intercept, when does the top equal 0? Well, only when x is 0, so there's only 1. It's also at 0, 0. The end behavior, remember, is a little tricky on these. You compare the degree of the top to the bottom. The top is degree 1. If I take the square root of x squared, I also get degree 1. So they're tied, so we take the numbers out in front. So it's going to be y equals, but if there's a radical involved, remember it has to be plus or minus 1. And you have to check, because one way it will probably be positive 1, one way it will be negative 1. So let's check. I'm going to go as x goes to infinity. What happens to y? So plug in some really big positive numbers. If I plug in positive numbers, the top would be positive, the bottom would be positive. So oops, not infinity though, it goes to positive 1. Now see what happens as x goes to negative infinity. What happens to y? Well, if I plug negative numbers in, the top will be negative, the bottom will still be positive. So it goes to negative 1. So just remember with radicals, you get those two different horizontal asymptotes. So you have to just test it and see what happens. Okay, let's find the relative max and min points and points of inflection. Let's put that stuff down here first, though. There's going to be, as I go to the left, horizontal asymptote at negative 1. As I go to the right, horizontal asymptote at positive 1. There's an x and y intercept at 0. And I think that's all the information we have so far. Okay, so let's go back up here. First derivative, we're going to say, when does it equal 0 or undefined? Well, it'd be undefined when this equals 0, which that never equals 0. The top will never equal 0 also. So there are no critical numbers. So really, if I did my first derivative number line, there's no critical numbers. I just want to find out if it's either always going to be positive or negative. Well, this graph, no matter what I plug in, the top will be positive and the bottom will be positive. So this graph is always increasing. So there's no relative maxes, there's no relative mins, but we do know the graph is always increasing. Okay, look at your second derivative. The bottom will never equal 0, but the top will equal 0 when x equals 0. So I've got a possible point of inflection at x equals 0. Do your number line. Plug in a number on either side. If I plug in negative 1, the top's positive, the bottom's positive. If I plug in a positive 1, I get a negative for a positive. So there's a point of inflection at 0, 0. And to the left, it's concave up. To the right, it's concave down. So I need it to the left to be concave up like that. To the right, concave down like that. And that's what my graph should end up looking like. So again, most of this stuff we've done before. In fact, mostly this graph we've actually done before. All we're adding is just a little more information by doing the calculus. You won't have to memorize the steps as far as the curve sketching recipe thing we have there. You just have to know how to find all those things. Similar to what we had on the very first test we did. Again, all we're doing is adding the relative max, relative mins, and points of concavity. All right, thanks guys.